Welcome to the Audio Architect Soundweb London Configuring Logic Part 2 Overview video. In this video, we'll run through a few exercises building logic circuits according to a set of criteria. We'll use some of the logic objects we learned about in Part 1, and we'll also use a few we didn't see. For Exercise 1, let's go ahead and build a push-to-talk button for our microphone. So if a button connected to a GPI port is held high, then we want the microphone to be unmuted. Otherwise, we want the microphone to remain muted. Now, technically, we could do this without logic, but it never hurts to learn a few new tricks. Within the Configure Audio section, we could use the mute for the microphone either from the input block or a gain object further downstream. Let's open the control panel for the gain object. Next, let's navigate to the Configure Logic section. So let's remember, the goal of this logic circuit is to unmute the microphone based on a response from another button wired to a GPI port. Let's use a logic source to begin our circuit, and we can name this to GPI1 since that's where it will be assigned. Now we need a logic object at the end of our circuit to link directly to the mute. A logic end is an excellent choice. Let's name this mic mute. Control drag the mute onto the logic end, and let's not forget to rename our link. Now, some of us may be tempted to wire the two objects together at this point, but if we do that and test it, we find the logic source is turning the mute on when it's pressed. We want the opposite to happen. We can use a NOT gate in between the two objects to invert the functionality. So now when the logic source is pressed, the mic mute is turned off and will allow a talker to pass through. Notice the numbers on each logic block? This represents the run order. It can be turned off if desired from the logic ribbon. When assigning the logic source to the GPI port, just remember to set its mode to direct action. Every Soundweb London device that can be configured in Audio Architect features a locate button. Some devices even have two, one on the front and another on the rear, though they are internally the same. Unfortunately, the devices do not have a dedicated power switch allowing us to easily cycle power and reboot the device. Let's build some logic to use the Soundweb London's device locate button to reboot the device itself, and moments before the device starts the reboot, let's mute the amplifier to prevent any unforeseen clicks or pops as a result of rebooting the DSP. Now, a device's locate button is bidirectional, meaning it will flash on if the device is located from Audio Architect or NetSetter. But if pressed on the device, assuming it has been matched to another in the venue, then it will locate the device in the software. We don't want to lose the ability to locate the device in the software from the hardware, so let's configure the logic so that the locate button must be held down uninterrupted for 3 seconds before muting the amp and rebooting the device. Let's also build a secondary button that can be used in the software or another controller to initiate the same process. Alright. So accounting for the software button is easy, as we've seen multiple times we can use the logic source. This could then be assigned to a custom panel, a Contrio controller, an iOS motion control panel, or even third-party control. Let's name this to locate override and turn on its auto-off feature by setting the time to 1/10 of a second. The reason we are doing this is so that the button will not remain on indefinitely. Another reason for enabling this feature is to have it behave a bit more like the locate button, considering it does not latch but is momentary. Next, to account for the device's locate button, we'll look in the available source options, and lo and behold, we find a logic locate. This is automatically associated with the locate parameter of the device hosting this logic. Now, to require that the locate button be held for 3 seconds, we can use either the delay or time delay object. Let's use a delay, and in the properties we can set the delay on to 30. Remember, we're multiplying this integer by 100 milliseconds. 3000 milliseconds is equal to 3 seconds. We'll leave the delay off at 1/10 of a second. Let's now account for what we want to happen as a result of the logic source or locate going high. To mute the amplifier channels, we could use a logic end linked to the amplifier mutes, but we already have a parameter preset created to mute both amp channels, so let's make use of that. Let's drop in a preset trigger and name it amp mute. In its properties, let's configure the active preset on 1 to recall the amp parameter's mute preset. Now to reboot the DSP, we can search high and low and we won't find anything in the logic objects that remotely says reboot. We'll end up using a logic end. Let's rename it to reboot. Next, let's click on the Custom Events tab and then click to Edit Custom Events. Here we'll find two events for input 1. When event 1, or in other words, input 1 is high, we want to reboot the device, so we'll type in $reboot and click OK. Now for either of these events to react accordingly to the locate or logic source, we need to place a gate in between the objects, and the keyword we're looking for here is OR. Let's wire the output of the delay and logic source to the inputs of the OR gate, and then we can split the output of the gate into the preset trigger and logic end. Let's test this out. We can use the test override feature in the logic locate. Let's set it to forced output high to verify the delay works and pay close attention to the end. Did you notice how both the preset trigger and logic end turned on at the same time? We want the amp mute preset to turn on before the reboot is initiated. How can we do that? We can use a single pulse trigger. We'll set its off time to 10, giving us 1 second before the output turns on, according to seeing its input go from low to high. And we'll leave the behavior set to ignore input during pulse because we're just toggling the input on. We're not leaving it on indefinitely. Okay, let's now rewire accordingly and test once more offline. Now let's use the logic source. It'll be quick, but we should see the preset trigger activate before the logic end. If for any reason logic is not behaving the way we believe it should, then we can always try using the reset logic option in the logic ribbon. Let's move over to testing this online, and don't forget to verify your Soundweb London preset proxy is set in the amplifier. Alright, now we're online with both devices and viewing each within the room. As we can see, we also have the amp device panel open in addition to our locate override control. Activating the locate override, we see the amplifier mutes turn on and the DSP falls offline due to the fact that it's rebooting. It should only take a few moments for the DSP to come back online. Great. Let's go offline and look at building a few other examples. In some cases, we may wish to control a third-party device using our Soundweb London processor. This can be achieved using serial or IP commands. Let's set up some logic to allow the Soundweb London device to send mute and unmute commands to an AMX SVSI encoder, assuming a connection can be made to the device. In our logic configuration, let's drop in an Ethernet trigger table. The Ethernet trigger can be used for protocol types of TCP or UDP. When the connect input goes from low to high, the Soundweb London device will attempt to create a socket connection to the third-party device at a specified IP address and port number. When connection to the device has been established, the connected output will illuminate, meaning we can then confidently issue commands to the third-party device. If a connection has been lost, as long as the connect input is held high, the Soundweb London device will automatically retry every 30 seconds to re-establish a connection. In some instances, a socket timeout can take up to a few minutes, so it's generally a good idea to be able to use an object that can toggle the connect input from high to low and back to high in order to request a new socket connection. When using UDP protocol, the connect input is ignored and therefore not required to be held high to establish a connection and issue commands. However, commands sent using UDP are not guaranteed. Now let's turn our attention to its properties. To send a mute or an unmute string, we'll leave the number of inputs at 1, and let's change the mode of operation to list. In the IP address field, we'll enter the IP of the device we want to send the commands to. Note, it's a good idea to use static IP addresses when controlling devices. Once online with the Soundweb London processor, we won't be able to change this address. For the port info, AMX SVSI devices use port 50002 to receive TCP IP commands, and in this instance, we'll leave the type set to TCP. Now let's enter our commands. Click to edit the Ethernet table, and we find we have input 1 off and on. We can enter commands using ASCII, decimal, or hex. Thankfully, the AMX SVSI API is easy to follow and allows us to use ASCII. For input 1 off, let's type the command unmute, and for input 1 on, mute. Now, Soundweb London devices will not add a carriage return automatically, and 1 is required at the end of each command. To enter this, we can switch from ASCII to decimal or hex. If using decimal, we can enter comma 13, or in hex, we can enter the byte 0D. Switch back to ASCII, and we now see our new line, aka carriage return. Let's click OK and look at wiring the object for use. Let's add in a logic source and name it connect to encoder, and let's add a second logic source to control sending the commands. Let's name this encoder mute unmute. Now we only want to be able to issue the commands if a connection has been made, so we can make use of the connected output. Let's add in an AND gate, and we'll wire the encoder mute unmute logic source to the first input and the connected output to the second input. By default, the encoder will be unmuted, so once acknowledgement is received from the encoder, we'll be able to send the mute command. The AND gate will literally be the gate preventing us from trying to send a command when connection has not been made. Let's go online and test it. Now online, we can force the connect input high, and seeing the connected output transition from low to high, we know we can send a command. If we take a look at the encoder audio mute through enable, we can see that it's currently unmuted. When we send the mute command, we can't see the change in real time through enable, so let's momentarily close it. Let's issue the mute command, and now relaunch the encoder panel. Great! The audio is now muted at the encoder. Let's test the unmute command. Viewing the encoder panel, we can see the mute has been disabled. While online, let's take a look at the CPU usage meter in the default control panel of our Soundweb London device. If we see this readout above 90%, then it's possible that the logic will run a bit slowly or even fail to execute. If there's any time-sensitive logic, then we should attempt to keep this meter below 90%. To lower the CPU usage, we could look at reducing the number of control panels that are open, consider moving parameter links from one device to another if possible, or move logic from one device to another. If it's not possible to reduce the CPU usage and time-sensitive logic is required, then it may be necessary to consider a third-party controller. Speaking of time-sensitive logic, let's move offline and look at one more example. In the scheduler overview video, we saw how an amplifier settings could be changed according to day and time. Let's create logic to disable the amplifier outputs according to a daily schedule of 11 p.m. And at 9 a.m., let's turn on the amplifier outputs. The logic is very simple. We'll add a calendar object, and in its properties, we'll click to edit the calendar. We can create a schedule by clicking on the plus sign. Starting tonight, we can specify 11 p.m. and select to trigger the event off. Let's also select to have this recur every one day. Click OK, and let's click on the plus sign once more to add a schedule for triggering the calendar on. We can start this tomorrow and specify 9 a.m. every single day. After clicking OK, we can exit the schedule and add a preset trigger. For the active preset on 0, we can recall a parameter preset that's already been created to disable the amplifier outputs. For the active preset on 1, we can then choose to recall the preset that will enable our amplifier outputs. Now, I won't have us sitting around all day to verify that this schedule will work, and while we could build in a mechanism to override the calendar and test the presets, we should all be confident knowing how to do that. What we do need to take away from this, however, is understanding the difference between how the scheduler keeps track of time and how a Soundweb London device keeps track of time. The scheduler in Audio Architect will work according to the Windows system clock, while the calendar object will function according to the internal clock of the Soundweb London device. By default, a Soundweb London's device clock is set to the Coordinated Universal Time, and if needing to execute logic based on time of day, then its time zone must be set using the Audio Architect venue options found under the File menu. Here we can locate the appropriate time zone for the region and set the daylight saving rules. When going online, the internal clock of any Soundweb London device will be updated appropriately. This concludes our Part 2 overview. Thanks for watching.